Yes.
My words will be recorded. Okay. So I'm very excited to be able to introduce Rajan today, who is one of the most, maybe, I don't know, prolific lattice QCD people. He's also written lectures on lattice QCD, and I think he would agree that maybe we have a little bit of a friendly competition, although he thinks I don't do enough.
You don't get it.
And he's involved in several lattice collaborations, mostly focused on nucleon matrix elements. And my favorite one is the enemy collaboration, because I can call him a member of the enemy.
Yes.
Which is the nucleon matrix element calculation. Anyway, he's here to talk about a very interesting topic on the pion-nucleon sigma term, which is related to dark matter scattering. So I'll let you take over there.
Great, thank you. Thank you for having me. And yes, I wasn't aware of it when we gave this name NME, which stood for nucleon matrix element, until Songwoo Park, who's one of my postdocs originally, and now is with Pavlos in Livermore. He said, you know, every time we say some result, which is from enemy collaboration, people here say, oh, our enemies. So I had not quite made that association till he brought it up, that enemy rhymes with enemy. Okay, so today what I would like to describe is our calculation of the pion-nucleon sigma term. And this was a fun collaboration and calculation, which is part of our general calculation of flavor diagonal matrix elements, where the axial ones give you the spin content of the nucleon conjugate.
Oh, just have to click on the slide again with the mouse.
No, you can go back and forth.
What did you do?
You click on the slide.
On the slide.
It has to bring it back to the front.
Okay, so, all right. So I'm just going to today discuss the calculation of the pion-nucleon sigma term. And as I was saying that the flavor diagonal matrix elements give us, in the axial channel, give us the spin content of the proton. In the tensor, they give us the contribution of the quark EDM to the neutron EDM. And in the scalar channel, they give us the sigma term, but the matrix element by itself is what enters in a number of BSM searches, like, for example, dark matter nucleon scattering, where if you have the scalar channel, then you would be using the coupling GS as your coupling of this mediator with the nucleons, as long as the interaction is written as Q bar Q, then the relevant coupling is GS. But also less important in terms of the popularity, all the 5 tensor or Lorentz structures, if there was a dark matter coupling in any of those channels, the same calculation enters there. So if you wanted to look at that, somehow the mediator, the dark matter mediator was an axial particle, then it would be the axial charge. And if it was the tensor, it would be the tensor charge. So scalar is the most popular, but all these charges are important in that respect from the view of dark matter searches.
Sorry to interrupt. So is the strange clock still very important for this context?
Sorry?
Strange contribution.
So the sigma term is just for the UND core,
yeah.
But there is a second quantity which is called the strangeness content of the proton, and that is an independent quantity. Yes, and people are measuring it.
Okay.
The thing here is that this, the original genesis of the sigma term is it gives the amount of mass generated by the light quarks. And there is an implicit assumption of linearity, that these light quarks are light enough that you are, because what you're doing is you're calculating the matrix element at the mass of the up and down quarks, and then just multiplying it by the mass to say this is amount of mass generated by the light quarks, but it really should be the integral
Yes.
of the matrix element times the mass over that. And so so that because of the linearity assumption, you don't extend that to the strange quark. Okay, there are three methods to calculate the pion-nucleon sigma term. The first is what we call the direct calculation, where you calculate the matrix element of UU bar plus DD bar, the isoscalar, assuming isoscalar symmetry here, and then you multiply it by the quark mass. The second is to use the Feynman-Hellman relation, where the rate of change of the nucleon mass times the quark mass, or with respect to the quark mass, can be calculated by just looking at the nucleon two-point correlation function, and that also gives you the scalar charge. Then there's phenomenology, where people have looked at the pion-nucleon scattering and then extended that to the point using the Ching-Dashen theorem, and we will talk about that only to the extent that what are the results from this analysis and how does lattice compare to that. So everything I'm talking about today, we are going to assume isospin symmetry, and here I'm just very briefly flashing the status as summarized in the FLAG 2021 report, which means the cutoff date for that was December 2020. And there you can see that there is some, variation between the NF equal to 2 plus 1 and NF equal to 2 plus 1 plus 1 results, but that really is not something which I think you should pay attention to, because this calculation, when we were doing the FLAG review, there is this result which is published, but so we can't ignore it. But when we went back to the authors, they couldn't remember what they had done. This was 10 years ago now. So, and I presume the postdoc who did the analysis is gone, so they have no memory of, and they had two results published in that paper, one which is here and one which is there. So by and large, the consensus in the lattice communities, you get a pion-nucleon sigma term of about 40 MeV. And then if you look at the calculation, the ones from phenomenology, they are more like 60 MeV. So this has been the tension in the community, that lattice results favor a value around 40 MeV and phenomenology favors about 60 MeV. And here, since that FLAG summary or FLAG report, there have been a number of calculations. Most of them again get something on the order of 40 MeV. And here I would today make a case of why we get around 60 MeV, or we say this is our preferred value. And at the same time, if I do the analysis as has been done by everybody else, we also get the value of 40 MeV. So the main thrust of this talk is, why are we pushing this larger value, or what's the basis for that? Okay, so how much introduction do you want to lattice QCD? 0, epsilon, epsilon squared?
My guess would be epsilon. You guys should tell me.
Okay, I will give you my idiosyncratic introduction to lattice QCD, which is so starting point is the Wick rotation converts a quantum field theory to a statistical mechanics system. Then once it's a statistical mechanics system, all physics is there in expectation values, and they are calculated as the average over the path integral. So the path integral is extremely important. You calculate, and then after you've done the Wick rotation, sorry Wick, it's not your Wick.
I love this Wick though.
Yes.
Always gets my attention.
Yes. Is that when you do the Wick rotation, the spectrum stays the same. It's just that the time gets rotated in the imaginary direction. So anything we calculate on the lattice, which is the spectral quantities, are unchanged under this Wick rotation. And also any matrix element we calculate, which is in fixed time, is the same. And everything I talk about today is true. This is true, so I don't have to worry anything about rotating back and stuff. But at the same time, just want to point out that because of this Wick rotation and the fact that if you have some quantity you're calculating at a whole range of times, then you have to rotate it back, and therefore that's a challenge. And the class of problems which at the moment are still hard is things like response functions, finite chemical potential, where you need to worry about this issue of going into imaginary time. Okay, next, what is lattice QCD? It's just QCD put on a space-time grid, so no approximations are made in terms of degrees of freedom. They're still quarks and gluons. And the way is there that the fermion fields are put on the sides. The links connecting these sides are, you place SU3 matrices, which is the representation for your gauge fields through this exponentiation. So clearly when you do this exponentiation and you expand it, you will find that you get terms of order a squared and a cubed. So that's where the discretizations errors, one of them is coming from. The fermions are on the side, notoriously hard. We don't know how to deal with fermions in numerical simulations very well. But fortunately, because the action is bilinear in the fermion fields, using rules of Grassmann integration, we can integrate them out. So basically, when you integrate them out, that what happens is that the fermion part of the action, which is psi bar d psi, where d is your Dirac operator, you can integrate these out, and it basically becomes given by, if you first do the integration, you just get the determinant of the matrix D as part of your integrand, and then you can exponentiate it so that you can write a modified action, which is the gauge action plus the contribution of the fermions through this determinant. So the determinant is just a functional of the U fields. There's no more reference to quark fields. And so now your theory is purely in terms of the gauge links, and that defines a configuration. So the basic idea is you use this action just like you would in statistical mechanics. Think of it as the Boltzmann factor to generate a set of gauge configurations using e to the minus s as your weight. So this ensemble of configurations, we basically sort of just talk about it and or sort of, oh yeah, we generated these, but this is the heart of lattice QCD. And I'll try and explain this, that this is the statistical or stochastic representation of the QCD vacuum. And the most beautiful part I like about it is that the QCD vacuum knows everything about physics. And now it's just our job to pull it out and pick it out by probing it. So once you have these configurations, as I said, they are only a function of the gauge fields. And with this gauge fields on the lattice, what we do is we calculate the quark propagator. The quark propagator is just the Wick contraction of two fermion fields at site X and Y with spin and color indices, I going to J, color indices, A going to B. That's the full Feynman propagator going from a given point to the other. So at the time when we are integrating out the fermion fields, we also write down, say, if we want to calculate some correlation function. So here I've done a nucleon created at site 0 going to site X, where the nucleon interpolating operator is given in terms of the three fields. This is the simplest nucleon operator, local operator one can write down. Then at the time when you're doing that integration, you're also performing the Wick contractions. So the result of that is now everything which was in the correlation function of fermion field is now represented in terms of quark propagators. And correlation functions are just taking these quark propagators, taking the gauge links, tying them together in appropriate ways to make them gauge invariant correlation functions. And these things are called quark line diagrams, because you basically have each diagram is this quark propagator which you have written. So, but underlying this thing is that this quark propagator knows about all the gauge interactions. So even though we are just drawing these quark lines, this is a fully interacting or full Feynman propagator, which means all orders of gauge interactions have been taken into account. So this is where the theory is called non-perturbative. Okay?
Can I ask a question? Yeah.
Sure.
Oh, thank you. Just can I understand these propagators solved using this gauge configure ensemble as some sort of exact propagators with QCD, all the QCD corrections included non-perturbatively? I'm not sure whether I can understand this way.
Okay, so on each configuration, you have all your gauge fields, and you have the Dirac operator, which is a functional of them, and you invert it. So you basically are in this background field, you're calculating the propagator. So a given, let me come back to this and maybe say some more things and then probably either confuse you more or maybe answer part of the question.
Okay, thank you very much.
So the basic idea is that, yes, your question, let me come back to that.
Thank you.
Okay, so what I have done at the moment, so maybe this will answer your question. So what I've done is calculate the quark propagator, which is the upper part, right? I've taken, say, QQ bar, do the Wick contraction, that is the amplitude for a quark to go from point 0 to point X, right? You agree with that? That's just the inverse of the Dirac operator.
Yes, right.
And that's what you call a Feynman, or you call a quark propagator. Now what you do is you basically say, okay, I know how to do that. Now I'm interested in a two-point function of a nucleon. So I create the nucleon at some point 0 and I annihilate it. And what as I told you, that at the time when you do your integration over fermions, you're also doing the Wick contraction. So here I've shown you one example of the Wick contraction where I've contracted Q1 with Q1, Q2 with Q2, and Q3 with, or Q1 again with Q1, right? So those are the three quark propagators. So I've gotten rid of the quark fields. I've now written it down in terms of quark propagators, right?
Yeah.
Okay, so now your question, if I understand, at least I'm going to bring it, is I calculated a quark propagator, right? I've combined this in the form of a nucleon. How the hell does this quark propagator, which was calculated on a given background configuration, have any idea about QCD or all the dynamics of the gluons? All I did was calculated this and I put it down by tying it together. I'm going to use the same propagator. If it was the pion, I would do the two pion lines. If it was the delta, I would do the delta. How does the quark propagator know anything about all these complicated things of whether it goes into a nucleon or it goes into a delta or it goes into a pion? Does that give a, is that the question in some sense you're asking?
Yes, in some way, because I just feel like I just need some propagators, then I contract them. I can get nucleon, I can get pion.
Yes.
Which just like what I did in some
So
way. I know the exact propagator and I draw all these diagrams. I get
yes.
everything. Yeah.
So you get that, but the deep question is, how does a quark propagator know anything about a nucleon? You've calculated a quark propagator, right? And you've tied it together to get a nucleon. And this is where the beauty, and I told you that it's the vacuum of QCD which you get, which is the most important. Because once you do this on a given configuration, you're absolutely right, it knows nothing about a pion or a kaon or a proton. Only when you do the average over all gauge configurations that you construct that it's a pion or a kaon 2-point function. And so what is happening physically is think of your QCD vacuum with fluctuations occurring in it. So each configuration is giving you a snapshot of your QCD vacuum with fluctuations. Okay?
Yeah.
Those fluctuations can include a pion being created and being annihilated for a short period of time, right? In your bubbling vacuum. What you're doing by doing this is picking up or reinforcing those fluctuations which correspond to a proton. So that gauge average is the part which is telling you what state it is. Because there are all these fluctuations happening in the QCD vacuum. And what you have done by putting in this external probes, because remember, you're calculating the quark propagator on background configuration. You're not dynamically looking at the quarks, you're just probing the vacuum by putting in this quark propagator through the solution of the Dirac equation on each configuration. Then you combine it into a proton, it still doesn't know it's a proton. But then when you do the gauge average over all possible configurations, you're picking out those fluctuations which correspond to a proton. Had I done a pion, it would have picked out those fluctuations which correspond to a pion. So in principle, it's absolutely essential for us to get the theory and the results right, is to make sure that the vacuum we create is absolutely rigorous.
Yes, right. Thank you.
Okay?
Yeah.
So I can explain more later, but I'm hoping that this provides, this is something I love explaining it this way, that what is it? And now it's non-perturbative because you are allowing all possible fluctuation. You're picking out all the possible fluctuations from the vacuum, which means all forms of gauge interactions, which are there in a real proton propagating. So,
yeah, this is very helpful. Thank you.
Okay, so just to summarize, there are 3 steps. You generate a QCD vacuum, which in practice means you have an ensemble of gauge configurations. These are snapshots of the vacuum, which means you're doing it stochastically. And the question you can ask, how many do I need? I need 10, I need 100, I need 1,000. So for mesons today, most of us say, okay, 100 configurations give you fairly decent results. For nucleons, the answer is probably 10,000. Because, and I explain why. Next, once you have this vacuum, you calculate correlation functions, and I showed you how you do that by doing the Wick contraction, writing it in terms of quark line diagrams. And then I will next show you how from these correlation functions you can get matrix element. And the beauty is that in addition to the vacuum, the second thing lattice QCD gives you is your full Fock state wave function in which you can calculate matrix elements. So the N and N here, which I'm showing you, this neutron, what lattice is giving you is the full wave function. And this from quantum mechanics, you know that if you know the exact wave function of a state, you can calculate the matrix element of any operator within it, and therefore you can get the physics.
Roger, let me just, I don't know, I'm confused a little bit by the language. You said that the lattice will give you the full wave function, but it doesn't, right? It just gives you the matrix elements of that wave function.
No, you can calculate of any operator. So the wave function is the full wave function. How you probe it, you limit it.
But I think you can't access directly the wave function.
These are all stochastic concepts. The problem why lattice QCD is a black box. is you have no picture of what the vacuum is, you have no picture of what the wave function is. You can only, as you said, calculate matrix elements. But it's a full wave function.
You can calculate matrix elements from the wave function, but you can't calculate the wave function.
You have no representation or visualization or any understanding of that. It's a stochastic construct.
Okay.
And that's why lattice QCD is considered a black box. Okay?
Now, usually you do have quark model in setup, right?
No.
You have 3 quark.
That is, I'll come to that. I'll come to that.
So then another
No,
stupid
hold
question.
your thought, I'll come to that.
Okay.
Okay.
Another stupid question, where is the ground? So normally you write down, I know that, but normally when you write down the local operator, you do have ground there too.
Everything is there. Everything is there. So when I wrote down the quark line diagrams, right? Now I've shown you that what these quark line diagrams actually represent is all possible gluon exchanges because you have the full Feynman propagator.
Yeah, that's true.
You're not doing it in the free field theory, you're doing it in the full interacting theory. And the fact is you can say, oh, you did this one line. How the hell did you get this connection? That's the vacuum fluctuations. That when you put the 3 lines together, you are putting up those fluctuations which correspond to these exchanges. That's what you're pulling out of the vacuum. And once you do that coherent sum, you get it. Okay, so now to answer your question also. So, okay, you calculated this correlation function, now what? So let's take the case you want to get the matrix element of the axial current within the nucleon state. So this is what you would write down, whether you're doing nuclear physics, high energy physics, this is the correlation function you would need to calculate. You create a nucleon, you let it propagate for some time t, and then you annihilate it at a later time, right? So now what you do is, you break it up into discrete units of time because you put it on a lattice, and at each discrete interval, you put in your transfer matrix, which is e to the minus the h times delta t, and a complete set of states at each intermediate time, where the states are eigenstates of the transfer matrix. So you do that, so you start with this vacuum, where you have not said anything about, I've just put a 3 quark operator, but that 3 quark operator has a coupling to the nucleon. It's not the full coupling, but it has that's all I need, is some coupling. So at least it couples. So then I say, okay, it couples, it creates a whole bunch of states which have the quantum numbers of the nucleon, and then they keep propagating, and each time they hop, they get an energy suppression or energy thing, e to the minus delta t. The amplitude decreases by that because you are in Euclidean time. Okay? So after a certain amount of time, this accumulates, and you get an energy suppression of the interval between your source and sink. But all your states are there. And that's what I call it, that this function after time t, the state ni, has the full Fock state wave function because all the states which couple to through this operator n are allowed. But each one is propagating and present with this energy factor. So if you now went back to Minkowski time, this is exactly under time evolution, each state would have been going e to the I omega t. And at any given time, there's a different interference between the various states, and you would get in that case, it's the interference, here is the exponential damping. So you have a state which has all the terms in it, each one being damped by e to the I t. So in that sense, it's the full Fock state wave function. But you have you have no idea what this looks like. You couldn't say it's a Gaussian, you couldn't say anything, we couldn't even tell you what a model it is to model it. We just know that we have it. And that's the stochastic. So now within the state, you can put the matrix element. Then on the other side, you again do the same game of hopping each time, and you build up this energy factor, and then in the end you annihilate it. So these connection of vacuum to the state through this operator are called the amplitudes, which are on both sides. And this part in the middle is the matrix element. So that's how you, the lattice QCD allows you to calculate matrix elements. Okay? All right. So now let's give some examples. Suppose I want to extract a nucleon charge. I want to extract Ga. So what I do is I'm going to assume that I have my spin aligned in the 3 direction, which is why I'm taking the third component. Then I have this 3-point function, but this 3-point function has these amplitudes and has these energy factors. But if I restrict my sum to just the ground state and 0 momentum, then these factors calculate the amplitudes, this energy cancels this one, and all I have left is the matrix element. And this matrix element, if you expand it, is Ga times gamma 3, gamma 5. I've basically ignored that. And so you can see that if I take the ratio of the 3-point function to the 2-point function, I get rid of all the amplitudes, all the energy factor, and I just extract the matrix element, and that is proportional to Ga. Okay? So the game is understanding these amplitudes and understanding these energy factors in order to get the matrix elements. So what are the challenges? I mean, this is very simple. Today, I mean, an entering graduate student or even a smart undergraduate can do this. It's almost become brain dead. But even though it's brain dead, we have challenges which are mostly in terms of getting precise answers. The first I'll show you is that the signal dies exponentially. So you can't separate these nucleons by large distance. And therefore, you can't just make this assumption that you've gotten rid of all the excited state contributions. And anybody who's done these calculations, you typically will see graphs like this, that as you take this tau large enough, larger and larger, you see the data looking like this. It goes down, in this case, on either ends, because close to the ends, the excited states contribution is larger, because you have a smaller energy damping factor. Then it's best in the middle, and then on the other side is again large. So this tells us that there are excited state contributions. So we have to handle those. So the simplest way is you take tau large and get rid of exponentially. You can increase your tau. Signal of higher states is dying off exponentially, so you can isolate them. But the problem with nucleon matrix element is, unfortunately, the signal is also falling. And so you have this competition between excited states and the statistical signal. The second problem compared to, say, pions and stuff is that in the case of nucleons, the mass gaps are small. The Nπ or Nππ states start around 1200 MeV, which is around the delta. And that mass gap is small. But worse is, it's not a single state. As you take the K, the relative momentum large, this is an infinite number of states. Now, on the lattice, initially it starts off with finite because momentum is quantized. So the question comes is, how many of these states contribute? Do they even contribute? Do you even need to worry about multi-hadron states? And I'll explain the reason why. So the only tool we have, and that's a rigorous tool, which I told you, you do the spectral decomposition, you have this answer which includes all the contributions as a sum over I and j, but how many of those do you keep? And then the final is, whatever we calculate on the lattice, we have to now extrapolate to the continuum limit, the 135 MeV, and infinite volume. So those are the things we need to make sure we've done right. So why does the signal die? So this was originally sort of clarified by Parisi and Lepage, that if you look at the nucleon, it's 3 quarks going, and the signal is going, falling off, as I told you, e to the minus the energy of the nucleon times time. If it's 0 momentum, it's the mass. Now look at the variance. You take this, the diagram, and you take its mod, its square, the mod squared, and you now have 3 quark lines and 3 anti-quark lines. The lowest state you can create out of that is 3 pions. So at long distances, the thing which will survive is 3 pion signal. So the variance is falling as 3 pion mass, and the signal is going as the nucleon. So therefore, the signal to noise degrades as nucleon mass minus 1.5 times the pion mass, which is 700 MeV, which is huge. So you're stuck. So if you want to resolve a small mass gap, which we said was small, which is 250 MeV, then you need large separations. But the large separations have this problem. So and here is a typical example of the 2-point function. You see at some point, the signal starting to get noisy. How am I doing for time? Probably very slow. No, 20
started
minutes.
5 minutes late,
Okay.
so you have 25 minutes to get.
Okay. So what does the signal look like? What does the data look like? Because remember, in principle, in theory, we know there's no assumption, there's no approximation. Here's your spectral decomposition. You have unknowns, the amplitudes and the energies associated. If you're smart enough, you calculate it, you fit it with this, you can extract everything without any approximations. Is that okay?
You mean only statistical?
Only statistical errors. Okay, so what does the data look like? So I'm looking at the scalar. This is when you put just the U quark. So U bar U. So you can see clearly, as I showed you, that as you increase the value of tau from 8, 10, 12, 14, 16, your signal, your data is going up. And this is an indication of excited state effects. You look at the D quark, very similar, it's increasing, so it's converging from below. So if you had not worried about excited states and you had done the calculation and picked up this number, you would have gotten a much smaller value for the isoscalar charge.
So what are the different colors of these points?
The separation between the nucleons, how far you're separating them.
Oh, and the
And then-
times where I measure the charge.
Yes, and
Okay.
this is where you insert your operator.
Okay.
The T is the
Yeah.
time of the operator, the color is the separation between the 2 nucleons. So now you add the up and down quark, both of them are going in the same way, so the excited state effect in this case acts. And now if you look at the isovector charge, it subtracts. And now you get a mess where you really can't resolve it because the 2 effects are canceling and all this but this is a statistical thing because in some sense the excited state in this case should be a small effect. The next thing is, which is again unique, that if I look at the disconnected part of the contribution, that also has a huge excited state effect. This is not true for the axial, this is not true for the tensor, the scalar is this huge effect. And I will explain or give you at least my reason for it. So then if you look at the total, which is what we calculate for the sigma term, which is U plus D connected and U plus D contribution to the disconnected, which is why there's a factor of 2 in the isospin case.
So I'm confused. So if I take the sources apart from each other, shouldn't then the excited states, which are the signal, when I measure the signal in the middle, the excited states be less important?
Yes, yes,
So but then I don't. So but your curves go up.
yes.
Oh no, they go down. I'm
No,
sorry.
the curves are going up.
So but then
So this is,
then how can you?
yes, so just 1 minute. So when we do the fit,
Yes.
okay, sorry, I've gone way. I'm showing you, when we do the fit, this is our asymptotic value. So you're starting with small, going up, you're converging towards that.
Okay. So why should the signal go up when the excited states go down? I
It
think
just, the amplitude.
it just happens to be the case.
Yes.
Okay. All right. That was
Yes.
my question actually.
Yes.
Okay, very good.
It's somewhat, maybe not completely
Yeah, I know.
theoretically
I'm
understood,
being-
but it's universal. They always seem to, the excited states seem to make it smaller, sort of.
Not all cases.
I could
Tensor goes the other way
I
around.
could imagine where things
Tensor
go.
goes the other
Yeah,
way
yeah.
around.
There's
Axial-
many different matrix opposites
Exactly.
go up or down.
Yeah, yeah.
Yes.
It's just some of
But for
different
this-
terms.
Yes,
Scalar and axial, they seem to always come from
Yeah.
below.
Okay.
Yes.
All right.
so axial and scalar come from below,
Okay.
tensor comes from above. So it's just the sign of the amplitude of the ground versus the relative.
Exactly.
Okay, so I've explained to you that this is the signal, so you can't argue that there isn't excited states. So you have to deal with it.
But that, I mean, but this is not like, there's nothing universal. I mean, the sign depends on your operator basis,
Yes,
and your volume,
absolutely.
and your quark mass, right? There's nothing like, it's just accidental that I mean, everybody has been using like quark model operators, and so the fact that everybody's seeing this like trend is just an accident of the types of operators, right?
Yeah,
There's nothing-
It's for this particular operator.
That's good.
Everything else is universal, it's just that I have to say it's for that operator I took into, for creating my nucleon.
That's good.
If I had a smart operator, yes, then I would have smaller excited states. That's the general thing we've learned in quantum mechanics. You do it smart, you get less contamination.
That's good.
Okay, so the basic thing is we have at least up to tau equal to 16, which in this case is about 1.4 for me. We have large excited state effects. So we have to do a fit to that spectral decomposition to get the result. Okay, so I just summarized what I just said. So now the question is why in this case, the disconnected contribution is large. So after struggling with this and thinking about it for years and promoting this whole thing, I realized what an idiot. People have known all the cases where you should be expecting an enhancement. So in the case of the axial current, which is the form factors for the induced pseudoscalar and pseudoscalar, it's been known as PCAC, the pion pole dominance. We know the current couples to a pion very strongly, and the pion couples to a nucleon, so that matrix element is enhanced. We've known that for 70 years. We've rediscovered the wheel. In the case of the sigma term, we know that there's a strong condensate which couples to two pions. So we've known that there is a strong coupling of the scalar current to the condensate. So therefore, this matrix element is going to get enhanced. We know that in the case of electromagnetic form factors, but there it's the vector meson dominance, but the rho mass is heavy, and so we expect it to be a smaller thing, but if there is we've known about it. So at least the three cases which are obvious, we've known about it. The same thing actually turns out in EDM, in the theta term. We've known for a long time the CP violating G0 part, that coupling is large. So we know that, and that also comes from a pion loop, where you put one of the CP violating couplings there when it attaches to the pion. So we know that likely that Nπ will play a role in your CP violation. So we've known this in different forms in phenomenology, and we've basically are seeing it in spades in lattice calculations.
Sorry, Raj, I'm confused, because you started talking about trying to explain why the disconnected piece is
Yes.
enhanced, but the disconnected piece, I mean, you separate the correlation functions into two pieces, one of which you call connected because of how you evaluate it, and the other one which you call disconnected because of the way you evaluate it, both of which are unphysical. The
So
sum
it's
of
a
them,
sum- it's
the
a
sum
sum.
is physical.
Right.
The sum is physical, and that I can relate it to like
Yeah, but
dispersive
the-
analysis.
Yes, but the point
But I'm
is that when
confused
you
what-
calculate it, you're calculating these two quantities. And you can draw diagrams as to how that effect comes in. So in the case of disconnected, this is the dominant thing, that the current couples to a quark loop, which then basically acts like a pion. And so you can see a large, and this coupling is large, this is the scalar coupling. So it's, so you can think of it as N with a pion loop, where the scalar couples to the pion. But in the case of the axial, the loop, the pion loop is different. So here, what I'm saying is, here's your nucleon, you have your pion loop, and the scalar current couples to this. And that's your loop diagram. But the equivalent for axial or tensor is this. And here, this thing is getting enhanced because this is the picture of what is happening. And this coupling is large because that's the condensate.
So why is that when disconnected, I'm always getting disconnected when you guys
So
talk
the,
about
yes,
disconnected?
yes. So the disconnected is simply because
Quark line
in the
disconnected.
quark line, there is this current coupling here, and there is this nucleon. So in the quark line diagram, there is nothing connecting them.
So, but the pion in your lower diagram, in the Feynman does have quark lines, right? So that's
This one?
Yeah.
No, this is in the current perturbation theory in the pion.
Yeah. But there are quarks coming through the pion, and they don't run into.
No, so see, this is the real diagram. Which is,
Oh.
yes,
Okay.
which is that diagram drawn is this the same diagram.
So this is then the pion loop, and
Yes.
and then the axial vector attacks where?
No, the scalar attacks here.
Thank you.
If it had
Yeah.
attached to
Got
the
it,
other
got
one,
it,
then
got it.
it's connected.
Got it. Thank you.
Okay, so this is why it's there, and of all the communities, you guys should appreciate that you've known this all along. It's just that we were dumb enough and took a long time to figure it out, or see it in the data and then figure it out. Okay, so we are back to this. We have got to do this whole fit in terms of getting rid of the excited states. And it's very clear that if you look at this isoscalar, which is contributing the sigma term, we don't see a sign of convergence. So you have to fit, right? Even the highest one is above the green. But if you look at things like this is the tensor, where you're looking at the iso vector or isoscalar part, then basically they cancel, and you see that. And here you wouldn't be making much of a mistake if you just took the average and assume no excited state. But here clearly you have to do the fit. Okay, so where is the resolution to this thing? So we did the fit where we took the amplitudes and the energies given by the 2-point function, and we got the result, which is the standard result everybody has gotten of 40 MeV. And it's also beautiful because this actually doesn't challenge anything. It just says, oh, there's this very nice linear behavior. The nucleon mass is linear in the pion mass or quark mass. Everything is hunky-dory. And then we put in the Nπ state as the first excited state. So this one here, the excited state mass is around 1500, which is close to the Roper. Here it's around 1250. And you see that the result is very different. This is 17, this is 12.
Okay.
But the part which is maddening is with our current data, from a purely statistical point of view, the chi-squared of the two fits is similar.
So what are the gray lines? I mean, you point to the.
These are the asymptote.
Oh, that's okay.
This is the asymptote, which is what we would call the result from the fit of the ground state. And now if you look at the chi-squared, this is 1.26, this is 1.20, 1.18, 1.19. So we don't have a data-driven way of saying, oh, is the Nπ there? There is one place where we actually have that, but in this case, we don't.
So the only thing is that you what? That you on the left-hand side, you have what? You have
The first excited state is considered to be the Roper.
Yes.
Here it's the Nπ.
And the Roper on top of it, or just the Nπ?
How many excited states?
You can put the dropper there, that
Doesn't make a difference.
that doesn't make it. It's really, I mean, it's which one is the first excited state. Right now,
Yeah.
our control is only over the first excited state. And it's the dominant contribution. The second excited state doesn't give you that enhancement like the loops I was telling you and stuff. It's basically coming from that pion loop.
Shouldn't that be a nucleon, a quantum number, this excited state?
It is. All of them have the
And the
nucleon.
Nπ I can cook into a nucleon?
Yes, with
Right.
minus k and plus k.
In a PUA.
Oh, okay, oh,
Yeah.
yeah.
Yeah, so when I say nucleon Nπ, I mean I've taken into account so as to get the right spin parity.
Okay.
Okay,
Sorry, can I ask a question?
sure.
So could you please explain again how to include these states, but do it by putting some prior on the
You
one
can do it, so in the case of, if I want to just do this calculation, I can put a simultaneous fit to the 2-point function and the 3-point function. The
Mhm.
2-point function will give you the amplitudes and the states
Uh-huh.
and the energies. And the 3-point function then is mainly giving you those matrix elements.
Uh-huh.
In this case, in the second case, where I'm saying Nπ,
Mhm.
because the data cannot distinguish, we actually do it through priors.
Mm-hmm. So you kind of fix the energy of the
Yes,
okay.
we fix the energy with a narrow prior.
Okay, got it. Thank you.
Oh, sorry, a prior with a narrow width,
Oh, yes, right.
which is essentially fixing the energy.
Oh, so yeah,
The-
oh, sorry.
Go ahead.
Oh, yeah, just after you fix the prior, for example, what are for example, the spectral weight of the for example, Nπ state in that case?
So
Is that
they are
small?
actually, at the moment, what we are seeing is the amplitudes are almost as large as the ground state.
Okay.
But I mean, we have to think more what that means. It's not straightforward that. So now, why did people not put in Nπ states?
Can I ask before though?
Sorry.
The reason you have this problem is just because your data is not that great.
Yes,
Is that right?
Oh,
You had
eventually.
pretty data,
Yes.
and you saw how it was cooling,
yes.
then this
So,
wouldn't rise at all.
so exactly. So right now, our goal for the next round of calculations is, suppose I could push another 2 sets of points. And at some point, the data will start to distinguish between this and this. And there are 2 ways. Raoul loves to say, "Oh, you idiots, put it in the right wave function."
I did not say that.
He's paraphrasing.
Yes,
He's paraphrasing.
and I am saying I'm too old to try and figure all that out. So I'm just going to go brute force and see if we can increase the statistics. So in the end, the answer will be somewhere in the middle. It'll be a combination of the 2. Okay?
But if I look at the particle data booklet, there is no Nπ resonance at 1.2 GeV. So
It's a delta.
Yeah, but that's not different quantum number than nucleons.
No.
This is,
It's Nπ.
it's really a pion-nucleon state.
Yeah, pion-nucleon state.
Assuming there's a finite volume state that has the mass, the energy is the pion.
I just have a
nucleon
nucleon floating around and a pion with it, and that's
Yes.
with no interactions and some relative.
Where you
In
show
some-
the interaction energy is sufficiently
Is
small
small.
that's within the uncertainty of the state you
Right.
extract. So you
Which
don't
is-
worry about the interaction.
It's probably not gonna be the case,
Yes.
but
So that's kind of nice.
No, with the uncertainty extracting an excited state this way, I think it would be the case. If you're doing a real calculation, it would not be the case.
So if you actually calculate it in a finite box, the Nπ state with the interactions, it will be slightly different from free nucleon and pion value. And what Andre just said, which is what we are assuming and seems to hold, is that difference, that interaction energy, is very small compared to 1200 or 1300 MeV.
Not only that, I'm saying it's small compared to the uncertainty with
Uh,
which you can
yes,
extract
yes.
that state.
So yes, so there are 2 things. One is it's within the uncertainty, and secondly, it's very small. So since it's a FET, the FET is really not looking at states. The FET just cares about what you put in as E1 and E2. I mean, that's the whole thing about FETs. They are totally blind.
yeah, but I can make a good fit and I can make a totally unmotivated fit.
Yes, so
And
here the
epicycles,
motivation
right?
is,
I mean, the question, am I doing epicycles or
Yes.
am I doing physics? Right?
yes, so the motivation here, as I said,
Yeah,
is a simultaneous fit to 2-point, because the spectrum which is created in 2-point
Yeah.
is got to be the same as in
Yeah, yeah.
3-point.
yeah.
So now why does this not show up in the 2-point? It turns out that when you do normalization of states and you take a local operator,
Right.
you have a 1/v spatial V,
Okay.
right?
Yes.
You put an Nπ state, right? You
Mhm.
get 1/v squared.
Mhm.
So there is a relative damping each time you go into a multi-hadron state in terms of the amplitude. And in all the cases where I said enhanced, what is happening is, yes, the creation is damped, but there is an enhancement in the matrix element. So it doesn't show up in the 2-point function, but it's important in the 3-point function. So the states are there. So once we do infinite precise thing, this method would work just as well, because it would also pick up the Nπ state.
So this Nπ state is not a resonance as I like it, but it's really a pion floating around in your box and a nucleon floating
Yes.
around, and just sort of a little bit talking
Right.
to each
And-
other, and that's it, right?
And when so another thing which has to be careful, when I say Nπ state, so pions floating around is perfectly fine,
Yes.
because your real world is a nucleon at one point and a nucleon and a pion and the full
Yeah.
Fock state wave function. The excited state is, which I'm calling excited, is when it goes on shell.
Yeah, exactly.
Because that, cannot happen in nature.
Right.
And but on a lattice it happens because energy is not conserved.
Yeah, but what would happen if you make your lattice if really large? Is that a finite temperature effect which you have?
No,
on your finite?
there's no fine, this is all.
Well, you have
zero.
a finite lattice house. You
Yes,
have
but
some-
the
that's not
temperature
the
is,
effect.
0 degrees essentially. Temperature is very tiny.
Okay.
It's not that, it is the equivalent of the temperature of a wraparound. It's when you say, what is the interaction between, say, a nucleon and a pion? Think of it just the finite volume. Think of it now as a mirror.
Yeah.
You enlarge it and have replication. Then it's the interaction between neighboring boxes,
Okay.
because a pion can wrap around, which is equivalent to jumping into a neighboring box.
Okay.
So the ideas are all what you're talking about.
So if I make my volume infinitely large, this thing should disappear. Is that right?
No.
You will have an infinite number of nearby.
So in the case of the axial, why it doesn't, so let me give you the reason, which is not so obvious here. But in the case of the axial, what happens is, if you can see this,
Well, I can throw in a 1.2 GV, I can throw in always a pion without any cost.
see, so what happens is, you have your current coming in,
Yes.
it connects to a pion,
Yes.
and this pion now eats up the pion which was created along with the nucleon.
Yes.
Since this is light,
Yes.
this interaction can happen anywhere in that 3 spatial volume.
Yes.
So the 1/v which you got
Right.
is now killed by the V factor which you're getting because the pion is light.
Okay.
So in the case of the scalar, it comes in is because this coupling is large. And you still have 2 pions going in that, again, it's a light pion compensating for that volume factor. So we are beginning to understand why this whole thing works. But it's something which you guys have all known about it in different ways. Thank God Kefe is not here. His language I never understand, but it's the same idea.
He calls it disconnected C.
Yes, and that is wrong. That I'm sorry is wrong. When he starts talking about disconnected C, because as Rahul said, nature cannot do connected and disconnected differently. I mean, it's the total quantity you calculate, but Kefe is smarter than me, so the question is, we are still at this point of what states contribute. We've included the first state and stuff. Next, we did a chiral perturbation theory analysis to see how big would this effect be. And it turns out that you can write it. So this is an Nπ, which is exactly what I drew. This is the lowest order. And this is the Nππ. Because you can also have the nucleon creating this pi. So it turns out in the case of the sigma term, the lowest order, if you just look at it, I mean, the chiral perturbation theory says both of them give about a 10 MeV effect. But the worst part is, it says in the chiral perturbation theory, up to momentum 3, so +1, -1, +2, -2, +3, -3, each one of them contributes at a reasonable level. And that is hopeless. If you think you can make a wave function with 3 different momentum states, it will be in. No, even you would have to pass it to your kids. So that's a long thing of trying to put in all these different states. So chiral perturbation theory also tells you that, look, both these states are going to contribute. And it's at the level of 10 MeV in each. And that's what.
Why do you think it's that far away? I mean, how many operators do you guys include in your delta GVP calculation?
I don't remember, but we have also now added the 2 pi and 1 nucleon.
2 pi and 1 nucleon, but like multiple Nπ operators.
Yeah, I don't know off the top of my head.
Yeah, I mean, I don't know. I mean, this is kind of standard now in the 2 meson sector, and the 2 meson barrier is not so crazy.
I had this wonderful conversation with Martin Savage, where I met him in 2005, and he was describing his whole program for nuclear physics. And we were saying, he said, so how long do you think it will be before we get results? I said, well, about 15 years. And his answer was, well, speak for yourself. So I met him 15 years later and I said, so Martin, what happened? He looks at it and says, I guess you were right.
It's kind of surprising that the 2 pi diagram is so important, because you would associate that with the sigma. That's got a 660 MeV mass.
Right.
So it's not really a long range interaction out there.
Well, this isn't really that. It's 2 light pions.
Yes. See, remember, these are 2 pions in a box.
It's really.
That's why I keep telling you, don't think of states.
It's not a resonance of the
So you're
nucleon.
saying that the sigma mass in a box is actually lower?
No, it's not the sigma resonance.
It's 2 pions coming on shell.
Yeah, it's really the operator creates the state, which is nucleon.
That's which operator is that? The axial operator or the nucleon source operator?
Nucleon source.
Exactly. Okay, good. That's what I thought. All right.
But the current can couple.
Oh,
if
you
you go
can pick it
backwards
up,
by-
of course.
Yes.
the current
And it
hits
kills
the
those
2
1
pions.
over V factors.
That's
And so it's not really like a sigma resonance interaction. It's really like these 2 pions that haven't formed resonance, but they're really have an energy that's
Right.
close to.
So the
2
sigma,
pions.
so the scalar operator creates 2 pions.
Yeah.
It doesn't know anything. I mean, see, the part in these fits is choose the worst case scenario. If you can justify it, it creates a operator like a thing, and that goes, it works. If you just say, forget about the sigma, it's just 2 pions.
So this is like the distinction in ordinary nuclear physics, that it's the correlated 2 pi that's the sigma. And then it's the latter, it should be uncorrelated 3 pi, which is much more important actually.
So, okay, so then I'm not going to talk much. There's a renormalization issue because it's a scalar quantity and we've done the whole calculation. The weakness of our result is that because it's this Nπ, you have to be close to the physical mass to see its effect. Because if you're sitting at 200 MeV pion, the difference between the radial excitation and the Nπ is very small. So this calculation really requires calculations, or anytime you have an Nπ effect, to have data close to the physical ion mass. So here we are showing you fits of what happens, and almost whether this is going to go straight, which is this gray curve where we don't include higher orders, or it's going to catch this curve, is in the one data point close to the physical point. So that's the weakness.
Would you like to have 180 MeV ensemble?
We have those in, but
No, on the ISK.
yes,
Okay, we'll talk later.
okay. No, but before I have that ensemble, I need a postdoc. So you're going to send a postdoc along with it.
Some money.
Yes, money is not the issue.
Oh, really?
Yeah. I can pay for the postdoc. I can't find the postdoc.
we do-
You guys should know how lucky you are. You're sitting in Berkeley. The draw of being in a place like Berkeley.
Good coffee.
It's not coffee. It's many times the two-body problem. It's the whole shebang. And the sex appeal. So in the end, okay, so here's the summary. Our result with the Nπ, which we say is motivated physics, gives us a value around sigma, which is consistent with the phenomenology. If we don't put in that, we get 40, which is consistent with all other lattice calculations. And that's where the story stands. So, thank you.
Any further questions?
Now back to my original one, so a strange quark contribution.
We have the results. The paper is under preparation,
Okay.
but I did not add it to this. So it's a reason for me to come back.
Is it 45 MeV?
Hmm?
Is it 45 or 50?
I'm not going to say a word.
Very nice.
I haven't seen any burning questions. So if anybody has time and is interested, Raj and I are gonna go get dinner at a Japanese ramen shop down the hill. You're all welcome to join us, anybody who wants to. He has to scoot off to Slack tonight.
Yeah, but I can go
Yeah.
later. I mean, I'm not in a big hurry. I'm just going to go to the hotel and sleep. See, this time I did something never done before. I had my talks ready before I came. Because I knew I was going to spend time with Barbara, who's going to drill me about energy correlators. So I better not have. At least I've understood that now.
Okay.
And I'll send you the paper. She's actually tasked you. Make sure you explain this to Rahul so that I can go bug him.
Wait, the task is on you to explain it to me?
Yes.
Ah, okay.
But the task on you to do the computation,
Yes,
though.
yes. So I explained it to you, and then you are she's going to hound you to do the calculation.
That's good. Okay.
I have one.
And you know who did the first thing? I was impressed. The guy who wrote this whole energy correlation was Mardasi. I would have never thought he would have be the person. And so we started looking at that paper, and he does it for E plus E or anything, but just the whole idea. And then I said, oh shit, that is exactly what I thought. And now we have to figure out from the energy of a particle, how that is given by this integral over this Wilson line, which we were struggling with.
Now coming back to your talk, there's one actual question there.
Oh, sorry.
Oh.
Yes.
Hi, thank you for your talk. It was very interesting. I have a question about, so here you say the Nπ and Nππ contributions increase as you approach the physical point. So does that suggest that if someone were to simulate this at larger pion masses, but not at the physical point, and they perform the extrapolation to the physical point, are you suggesting that they would miss these larger contributions due to these states?
Okay, so let's do two calculations. Okay, we take say 220 MeV or 200 MeV, all right? And I do my continuum extrapolation. So I'm doing QCD with a 200 MeV pion, right? And I go to the continuum limit. Okay, so I will get a result which is true for 200 MeV pion. And in that, as I said, you will not see the effect of Nπ state. Unless you have very light. If you have infinite statistics, yes, you will see a small difference between the two fits. It'll be much smaller than what I showed you. Now you do the calculation at 135, this thing will blow up. Now you're saying, look, if I could do the calculation at 220, 200, 180, 160, yes, if I now did the extrapolation in the continuum thing, the small differences would grow as I went to 135, and the extrapolated value to 135 would capture the effect. But you would have to have very precise statistical errors to see that growth as you took the quark mass down.
Okay. All right, thanks.
It's this absolutely nightmarish thing of statistical versus systematic errors. Each one has to be done to the appropriate precision to get the effect you want.
I see. Thank you.
When you talk about contributions, again, these are excited state, unphysical contributions.
Yes,
Got it.
yes. If they are only on shell, when they're on shell, that's unphysical.
Yeah, sure.
Because nature, you can't have a nucleon and give rise to a physical pion. There's no radiation of a physical pion.
Sure.
But on a lattice, yes, because energy is not conserved.
No, but I mean, you can have transitions, right? That's where these are coming from.
No, not in a two-point function. There is no transition. A nucleon cannot become a nucleon and a pion on shell.
Sure, the 2-point function, sure.
I have one brief, somewhat technical question on your chi-square per degree of freedom when you're comparing. You use the prior in one case and not in the other.
So what, yes. And then
so
we
my
do-
question is, how do you count the chi-square per degree of freedom? when
Or
you
we
have
do
the
that
prior?
standard AIC.
No, but when you count the number of
It's
degrees of freedom,
it's the enhanced chi-square.
it's the augmented chi-square.
Oh, sorry, augmented chi-square.
But so the chi-squares you're comparing are not really the same. 'Cause
I
one's-
agree, I
okay.
agree.
Okay. That's all.
But I have no way of,
No.
we have no way of saying one is better than the
Not a
other.
criticism, just trying to understand what
Right.
you mean.
No,
Yeah.
yeah, it's the augmented chi-square.
Okay, just thank Rajan again.